Hi again, this is our last lecture on logic. And specifically today, we'll be talking about what's called arguments or symbolic arguments. Everything we learned before will be useful now, especially truth tables. And we are going to be able to justify if an argument is valid or invalid. And of course, before we do that, so what is an argument, how to construct an argument. And once we learn the elements of an argument, a logical argument or symbolic argument, then we'll be able to tell if it is a if it is a valid argument or an invalid argument. So yeah, we'll learn again to determine the validity of a symbolic argument using truth tables. And we are going to have some, well, the term is called here a logical conclusion from a given set of premises. So we'll do some laws. Let's not worry about that too much now. So the definition. So what is a symbolic argument? A symbolic argument consists of a set of premises and conclusions. So a premise and a conclusion, these are statements, logical statements. What's the difference is that a premise, it's a statement, a logical statement that is supposed to be true. So if I give you a set of statements, a bunch of, let's say, statements that are true, based on that, can you tell me if another statement is true or false? If it is true, then the argument is true. The whole argument is true. If it's not, it's invalid. So like I just said, an argument is valid when its conclusion necessarily follows from a given set of premises. A premise, it's a statement that is true. If not, we say the argument is invalid or it's a fallacy. I know this is confusing, what's going on here, but don't worry. Once we get to know how to symbolically represent things, the rest is just, it's a matter of truth tables. If you know how to construct a truth table, you know how to do this. And I hope now that everyone knows how to construct a truth table. And construction of a truth table is basically, you know, your laws, you know, how to do the negation or the conjunction, the disjunction, the conditional, and the biconditional. If not, then yes, you are going to be in trouble because you need to know the basics of truth tables. Okay, here is an example. I'm going to give you an example, and this example actually happens to be a law that is known by the law of detachments, or sometimes they're called modus ponens, those, you know, fancy words. Modus ponens is this law here. So let me write down the whole argument. Okay, this is how you symbolically represent it. Suppose that you have two premises. This is the first premise, and this is the second premise, and they are supposed to be true. Based on that, you see those three dots, you read them as therefore. Tells you if P implies Q, it's true. And if P is true, can you say that Q, is it true or false? If it is true based on this, then the argument is valid. It's not valid. Again, this is still not clear, I understand. But if I give you a real life situation, suppose P is snowing. Suppose that P is, it snows. Q is cold. So P again, it's snow. Suppose I tell you, if it snows, then it's cold. And now it's snowing. Can you conclude that it is cold? Well, of course. I know if it snows, then it's cold. Now, if it snows, of course it must be cold. And as simple as that, yes. And this law is known by the law of detachments or the modus ponens. Now, this example, I was lucky to be able to give you a real world example that depicts it. But what happens if I have 3, 4, 5 premises? By the way, we always have one conclusion. How many premises we have? Well, it depends on the exercise. You have 2 premises, 17,000 premises, but you always have one conclusion. So how are we going to do, for example, an exercise of 3 premises? it is not always, you're not always in obligation to find a real life problem so you can see or you can feel how it goes. There is a pretty straightforward method to check if this argument is valid or not, using what's called the truth table method. And it's pretty straightforward. So here again, it says if premise 1 and premise 2, then the conclusion. So here, premise 1 is this one here. This is, you copy paste your premise 1. You always and premise 2. If you have more premises, you keep saying and premise 3 and premise 3. And at the end, you put the arrow and you put Q. And you can construct the truth table of this one here. If the truth table of the whole thing happens to be giving you always true, which is called a tautology. Remember we talked about tautologies before? And the problem is that we'll be talking about them. Well, here I am. So what is a tautology? It's a statement that is always true. So if premise 1 and premise 2 implies, or if premise 1 and premise 2, then the conclusion gives you a tautology, means that the argument or the symbolic argument, or just for short argument, is a valid one. If it is not a tautology, then it is a fallacy or it's invalid. Well, let's build the truth table of this one here. Well, this is what I just said, right? So, well, maybe they give another example here. Okay, well, let's go slowly here. So it says here, write the argument in symbolic form. So, well, they give you the process. So how can, if you are given an argument to justify whether it's valid or invalid, the very first thing, write the argument in symbolic form. Sometimes they give you that in symbolic form directly, like this one here. They give you this symbolic representation directly. If not, if they give you things in words, well, the very first step is write the argument in symbolic form, right? Compare the form of the argument, which forms that are known to be either valid or invalid, or use the laws. If there are no known, that's the forms to compare, then, or you don't remember, then go to step 3. What is step 3? If the argument contains two premises, write a conditional statement of the form. So put your premise 1 and premise 2, and then the arrow conclusion. And then will be the next step, construct the truth table for the statement above. If the answer column, if the truth table has all truths, then the same is a tautology and the argument is valid. Otherwise, if the answer column of the table does not have all truths, if it only takes just one false, then the argument is invalid. Okay, well, let's do this exercise. I want you just to pay attention to this one here, and you will see how easy that is. It says determine whether the argument or the final argument is valid or invalid. It says, well, remember here, this argument that are given me here, it's not symbolically represented. So step number 1, I need to translate things to symbols first. Well, first of all, let's read it. It says, if you have enough reward points, then you get a free flight. You do not get a free flight. Therefore, you do not have enough reward. So what do you think, valid or invalid? So how many premises? You have premise 1, have 2 premises, and premise 2. And this is the conclusion. You see the therefore here? This is the conclusion. So first of all, let us convert these things into symbols. So it's going to be easy to work with symbols, and we'll go from there. So if you have enough reward points, well, having enough reward points is one statement. Get a free flight is another statement. So we have 2 statements here. So let P be, you have enough reward points. Let's Q be, you get a free flight. Then if I go back, you see the thing that I'm circling here, I'm putting in the box, you can symbolically represent by if P, then Q, the negation of Q, then the negation of P. So how many premises again? So you have the first premise, the second premise, the conclusion. Put the first premise, you always have and. You always have and the second premise, and then the arrow, the conclusion. And construct the truth table of this one here. If everything is true, so therefore it's a tautology, the argument is valid. If not, the argument is not valid. Well, now we're going to continue on the exercise, constructing the truth table of the whole thing. So we have 2 statements, P and Q, either both true or both false. The first one true, the other one false. First one false, the other one true. And we are going to construct the truth table of the whole thing. So we got to do, so the last column will be this one here, right? So this is the conclusion, the last column. If it is all true, then it's an argument valid, an argument that is valid. We'll do first one, right? P implies Q. Right? True implies true is true. True implies false is false. False implies true. So the second one will be this one, the negation of Q. Take these things and flip them. True becomes false and false becomes true. Now this one here will take place. True and false is false. False and true is false. True and false is false. And true and true is true. So the only thing in this column is true. Now it's time to do the negation of P, which is step number 4. Just flip the P. And now we're going to do this with this. So we are going to the last step with the fourth step, we'll do the arrow between them. So false, false, arrow false is true. False, arrow false is true. False, arrow true is true. True, arrow true is true. So it's going to be always all true here. So it is an argument that is valid. So that's the last step, number 5. It's going to be true all the time. And therefore, it is a tautology. And therefore, the argument they gave us is true. So since the answer, like I said, of column 5 has all T's, the argument is valid. Right? So what's argument again? This argument they gave us, this one here. Right? If you have enough reward points, then you get a free flight. Well, you do not get a free flight, or you don't get a free flight. What does it mean? It means that you didn't have enough reward points. That kind of makes sense. So, but again, please don't try just to do this exercise based on your sense. So you need to be careful. Some exercises are trickier than others. But once you translate things into symbols, and once you construct the truth table, you cannot go wrong. It's like this one here we just finished. Okay, the argument's valid. Okay. So there are laws, right? So there are laws that you can memorize if you want to. Let me put them all on the slide. So this is, we did this law called the modus ponens, the law of detachments. If you have P, then Q, and you have P, therefore you have Q. This is valid. If P implies Q and you have the negation of Q, then the negation of P is true. So this is called the law of contraposition. And some sort of called modus tollens. There's a law of syllogism. If P implies Q and Q implies R, then P implies R. For example, if it snows, it's cold. If it's cold, you wear your jacket. Then if it snows, then you wear your jacket. Something like that. And the last one is called the disjunctive syllogism. I know these words are a little bit tricky, but don't pay attention to them too much. It just recognize the laws. If you have P or Q is true and the negation of P is true, then Q must be true. He said today is Friday or it's snowing. Well, today is not Friday, therefore it must be snowing, because this one, the premises, in all these examples, you have 2 premises and 1 conclusion. So the premises are statements that are supposed to be true, or they are true statements. Okay, well, here's an example. Can you tell me if this argument is valid or not? Well, you can always, you need to have no room for any error, translate these things into symbols and go from there. But before we translate things into symbols, let's read it to make sense out of it. It says, if you are on Instagram, then you see my pictures. If you see my pictures, then you know I have a dog. So these are 2 premises. Therefore, if you are on Instagram, then you know I have a dog. So let's translate this into symbols. So P will say you are on Instagram, Q to say you see my pictures, and the dog thing is R, you know I have a dog. So if you symbolically represent things, you are going to have this. So P implies Q. If you are on Instagram, then you know, then you see my pictures. That's the Q. If you see my pictures, then then you know that I have a dog. Therefore, if you are on Instagram, then you know that I have a dog. So is this valid or invalid? So there are 2 ways to do this. If you recognize that this is one of the previous laws, and it is, right? Then you don't have to do the truth table. If not, we can do the truth table. Well, how are we going to do the truth table? We have two premises. So here's the first premise. You're going to do the truth table of P implies Q and Q implies R. Everything implies P implies R. So you can do the truth table of the whole thing. Well, here, how many rows are we going to have? We have P and Q and R. We have 2 to the power 3, which is 8 rows. So when you do 8 rows, it's going to be a long, long shot. It's going to be a long exercise. But trust me, at the end of the day, you're going to find that every row will yield to a true statement at the end. So this is the last step. So step number 1, you do this. Step number 2, you do this. Step number 3, you do this. Or step number 3, you do this. Step number 4, you do this. And the last one is step number 5. And when you see 5, you are going to see all the 8 truths. That's one approach. But if you look at this, is this making ringing some bells here? So if you look back to the laws, it is this law here. It's a law of syllogism. And we know laws are always valid. So it is a valid statement. So really, we don't have to do the truth table for this one because it is exactly of the form of the law of syllogism. So therefore, it is a valid statement. Here's another one. So again, but if you are curious to do the truth table of this one, you can always do that. Here's another example. Well, here's another example. Determine whether the following argument is valid or invalid. It says, if it is snowing, then we put salt on the driveway, right? So if it is snowing, then we put salt. Well, let me represent this. Snowing is P. If it is snowing, that's P. Put salt on the driveway, that's Q. We put salt on driveway. That's Q. It is snowing, P. So if I symbolically represent this, it says P implies Q. That's the first premise, this premise here. The second premise is Q, therefore P. So this is Q, right? So is this an argument that is valid? We can construct a truth table. Well, go ahead and construct a truth table. Put P implies Q. By the way, if you compare this with the laws, you're not going to see a law like this. So P implies Q and Q, everything P. So do the truth table of the whole thing, and you are going to realize that is not a tautology. That's not every entry is true. So I will let you do that. So if P is snowing, like I said, P is snowing, that's what. So I was lucky this time. I used the same letter for P. Let me see. Q is put salt on the driveway. In symbolic form, we are going to have this argument. So it is in the form of, well, it's a, we didn't talk about fallacies, but if you go ahead and do the truth table to see if it is valid or invalid. So in symbolic forms, well, this is another example. I'm sorry, I'm going a little bit too fast here. So if I go back to my example, if you do the truth table of this one here, you will realize it is a fallacy. Why? Because you're not going to have T in every column. And I hope I'm not confusing you here. Just go back and slowly write things down and pause it and work it out every time I ask you to do something, right? So when I say do the truth table, go ahead and do the truth table and then resume watching the lecture. So this is a symbolic representation and do the, so it is a fallacy. Well, they didn't show us using the truth table, but that's what I'm saying to you. Do the truth table to see if it's not, to see or to prove it is an invalid argument. Well, here's another example. If it is snowing, then we put salt on the driveway. If it is not snowing, therefore we do not put salt on the driveway. If we do symbolic representation again, to make life easier, so P is snowing, Q, we put salt on the driveway. This argument will be P implies Q, the negation of P doesn't tell me the negation Q is no. Do the truth table of this one here, and you will see that this is not a valid argument. So as I told you, it is invalid. Can you find out why? Well, again, I'm going to construct a truth table. I'm going to construct a truth table. This one here. P implies Q, and the negation of P implies the negation of Q. Okay, I'm going to do the truth table of this one here. So one column for P and one column for Q. Yeah, so I'm going to have what? True, 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 false, false, true, and false, false. And then I'm going to write the whole thing here, right? I'm going to write the whole thing, which is P implies Q, and the negation of P implies what? Negation of Q. So I'm going to do these things in steps. So I'm going to do, this is step 1, this is step 2, this is step 3, step 4, and the last step is this one here, right? Okay, if P is true and Q is true, true, arrow true is true. The negation of P is what? Is false, because if P is true, not false. And this is what? True and false is false. Now, what is the negation of Q is false. False, arrow false is true. So I got you true. So I'll keep going. Now, what happens if this, the final one is false? Then I stop. I can say, if I hit the first false, I stop because the argument is invalid. Remember, for the argument to be valid, everything must be true. Well, if I hit one false, then there's really no need to continue. All right, let's keep going. Now, let's do step number 1. If true implies, or if true then false. Well, this is going to be false. The negation of P is going to be false. False and false is false. Then this is what? Negation of false is true. False implies true is true. So it did go well for this one here for the second. Let's do the third one. False, arrow false is true. Negation of false is, the negation of true is false. True and false is false. And therefore, this negation of Q is false. This is true. Okay, and the last one. False, arrow false is false. Is false. Oh no, it should be valid here. Hold on a sec. P implies Q. And we have a negation. No, it's invalid, definitely invalid. Because I feel like I'm making an error somewhere, but I'm going to check everything. The negation P is true. This is false here. Okay, I made an error somewhere. Okay, I'm going to redo this. Okay, so this happens when you do things a little bit fast. Okay, I'm going to construct the truth table again. Negation P implies negation Q. This is, I know by experience that this is an invalid argument for sure. Okay. So let me take my time here. P and Q and the whole thing. What's the whole thing? It's P implies Q and the negation of P implies the negation of Q. Okay, here's my true, 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 false, false, true, and false, false. Okay, we change the color, so I'm going to do step number 1, step number 2, step 3, step 4, and the last step is this one here. Okay, we change the color for easy reading. So here P implies Q. If P is true and Q is true, P implies true is true. And the negation of P is false. And true and, see this is an and here, true and false is false. Now the negation of Q is false. False, error, false is true. So keep going. Now let's do this one here. True implies false is false. The negation of P is false, false, and false is false. And false, error, anything is, well, the negation of Q again is true. False implies is true. Okay, the third one. False implies true is true. The negation of false is true. This one is true. Now, what is the negation of Q? Is false. Aha. True, error, false is false. That's it. This is the one here. So I really no need to do this line here. So once I hit one F, so this is an invalid. So it says it is invalid. Can you find out? Oh, can you find out why? Well, we just did. Excuse me. Wow, that makes me sneeze. Yeah. So can you find out why? Well, yes, we just did it, and we find that it is not a tautology. Well, you just learned from my mistake. So I'm doing these things a little bit fast because I taught this quite a few times before, so I felt a little bit confident to go a little bit fast. But it is very repetitive, you know. Again, just you need to know your truth tables, the basic truth tables of the 5 operations: the negation, the conjunction, the disjunction, the conditional, and the biconditional. Once you know how to work with those basic 5 tables, trust me, you should be able to do everything else. It's going to be just a matter of new language, jargon. And sometimes when you are dealing with something new, it's always, you know, that learning disability we have. We are a little bit afraid of anything new, but just give it a little bit of time, get used to it, and you will be able to tackle it with no issues at the end. If not, well, you know what to do. Let me know. Okay,